Alright, so let us recall that we had this theorem which says that given a matrix M, its RREF is unique. EF is unique, alright. Fine. So, all of us are going to get the same matrix finally, and therefore, this plays a very important role in understanding the things. So, let us try to understand this using some example first. Example. So, suppose I have a system Ax is equal to B, where A is 3 cross 3 and X is 3 cross 1, B is also 3 cross 1. So, I have the augmented matrix as AB, fine, and suppose my RREF is CD, fine. Question is, what are the possibilities for C? So, question is what are the possibilities for CD, alright, fine. So, let us go by one, try to understand it. Now, this matrix has 3 rows, alright, and 4 columns. Now, since it has got 3 rows, how many pivots can it have? Fine. So, let us try to understand that. What the definition of pivot was that every non-zero row has a pivot, alright. It is not about A, the pivot is with respect to RREF. So, when you are saying that I am looking at RREF of AB, so I am looking at CD. So, I would like to see that in this matrix CD, the RREF, how many non-zero rows are there. It may happen that all the 3 rows are non-zero, or it may happen that so all the 3 rows are non-zero, 3 rows of CD are non-zero. That is the first choice that I have. Second choice, only 2 rows of CD are non-zero, and the C is only 1 row of CD is non-zero. So, I am not taking the case here when the whole matrix A as well as B is 0, that I am not taking. I am assuming also that for every variable or the unknown x, y, z, I have at least one non-zero entry with me, fine. So, that assumption is there with me that all the variables x, y and z or all the unknowns x, y, z have at least one non-zero coefficients with it. Is that okay? So, that I can talk of things here, fine. So, I have got 3 cases. This matrix has A has 3 rows, augmented matrix joins with me. So, there are 3 rows and 4 columns as far as CD is concerned. CD is an RREF. So, it can have all the 3 rows as non-zero, only 2 rows as non-zero and only 1 row as non-zero. So, in the first case what happens is I am assuming that all the 3 rows are non-zero. So, what are the possible pivots? So, the possible pivots are the pivots, pivotal columns will be in A. Either the first column is a pivot, second column is a pivot, third column is a pivot, or first is a pivot, second is a pivot, fourth is a pivot, fine. Or it can happen that the first is a pivot, third is a pivot, fourth is a pivot, or second is a pivot, third is a pivot, fourth is a pivot, fine. So, there are 4 columns, out of that any 3 can be a pivotal column. So, pivotal columns could be 1, 2, 3, 1, 2, 4, 1, 3, 4 and 2, 3, 4. So, let us write the corresponding matrices for us. So, if this is the pivot 1, 2, 3, then I need to get identity with me. This is what we had understood that in the previous class, that whenever we have a pivot, each pivot gives me some form of identity. So, since there are 3 here, so I will get identity here in the first 3 columns, and therefore, D will be something like D1, D2, D3, something here, and this will give me that the solution as x as D1, y as D2 and z as D3. So, I get a solution directly here, and this is a unique solution. Is that okay? So, I have a pivot, there are 3 pivots, and these 3 pivots, they are at position 1, 2 and 3. So, they correspond to the variable x, y, z, and therefore, I get a unique solution. What happens at 1, 2, 4, 1, 3, 4 and 2, 3, 4? Let us try to understand that part. Fine. So, here it says that 1, 2, 4. So, 1, 0, 0, 2 is 0, 1, 0, and the fourth one it says that 0, 0, 1. Fine. So, see again here that pivotal or the RREF is so important that the ones they are going to the right. Fine. The ladder like idea is coming to play. Fine. So, what will happen to the third one here? Third one here could be anything here, but it has to be a 0 here, because if it was a non-zero entry, if this entry was non-zero, so if this was non-zero, this would have become a pivot. Non-zero will imply a pivot, all right. So, that will give you a contradiction. So, therefore, this entry has to be a 0, there is no other choice for us, all right, fine. And this entry, whatever it is, that we are not bothered about, but this is how it is going to look like. So, here I would like you to see that this equation, it corresponds to saying that x times 0 times x plus 0 times y plus 0 times z is 1, and this implies no solution. I cannot find any value of x, y and z such that 0 times x plus 0 times y plus 0 times z is 1. Fine. So, in this case I do not get a solution. What happens to 1, 3, 4? Now, let us look at 1, 3, 4. So, I have got 1 here, 3 is the second one and 4th is the last one. Again, I would like to understand what is this entry. Can I say that this entry has to be a 0? Because if this entry was non-zero, again this will become a pivot, and that will again contradict that CD is in RREF, all right. So, this is important that we are doing everything with respect to CD. So, this has to be 0, because if it was non-zero, this becomes a pivot, this has to go up and things like that, fine. This will not be a ladder like. So, this is not a pivot, so it has to be a 0 here, because this is the pivot that I have got here, these are the pivots. So, this is a pivot, everything on the left of that is supposed to be 0, fine. This is what the idea was. In every non-zero row, the first non-zero entry is a pivot, all right. So, if you see again, I will get 0 times x plus 0 times y plus 0 times z as 1, and therefore, no solution here. Is that okay? So, again the same argument. Now, what happens to this one, that case 2, 3, 4? Here 2 is the first one, so it is 1 here, 0 here, 0 here, 3 is the second one, and this is the third one that I have got. Here again, if I look at, this has to be 0, because if this was not 0, then again this should have become a pivot and would have contradicted that CD is in RREF, all right. So, therefore, what we see here is that this case again leads me to the idea that 0 times x plus 0 times y plus 0 times z is 1, which has no solution, all right. So, you can see that from RREF I am able to conclude when the system will have no solution as such, fine. There are other ways also. Now, let us look at what happens to the case B and C. So, the case B is we have got only 2 rows which are non-zero. So, there are only 2 pivots, fine. So, now case B, only 2 rows of CD are non-zero. So, again there are 4 columns. So, out of 4 columns, any 2 columns can be pivotal columns. So, the pivotal columns will be 6 of them. So, either 1 2 or 1 3, 1 4 2, 3, 2, 4 and 3, 4. So, let us look at these things separately. So, what I know is that there are only 2 rows which are non-zero rows, and the 0 row are supposed to be in the bottom. So, last one is 0 here, 1, 2 here basically means that I have got 1, 0 here, 0, 1 here. There are no more pivots. So, there are some entries here that we do not know what they are, fine. Similarly, if I look at 1, 3, I have got 0, 0, 0, 0, 1, 0 here, fine. I also know that 3 is in the pivot. So, 1 is here, there is a 0 here. I do not know what these are. Can I say that this entry has to be 0? Because if this was non-zero, this would have become a pivot. So, this has to be 0, but I do not know what it is here, fine. Similarly, for this entry 2, 3, again look at it, the last one has to be 0, fine. Here there is a 0 here, because there is no pivot at the first column. Second column there is a pivot, and third column there is a pivot here, fine. And I do not know what they are. These are the choices that I have. But we had also assumed, if you recall, we had assumed that every variable comes with a non-zero coefficient, all right. Since we had assumed that every variable comes with a non-zero coefficient, so this case is not allowed basically because of this part, because it says that all the coefficients of x, all the coefficients of x are 0, which is not allowed for me. So, I can forego that part, all right. Similarly, for this 2, 4 and 3, 4, I will have to forego because that is not allowed for me, fine. So, now let us look at what is 1, 4 for me. 1, 4 basically means I have got 0 here, 0 here, 0 here, 0 here. There is a 1 here and there is a 1 here, fine. Now, this is a pivot, it means that all other entry in that row is 0, and therefore, this again gives me 0 times x plus 0 times y plus 0 times z is 1. So, I have got no solution, fine. And here these entries could be anything that I am not bothered, but this is what is going to happen. So, I would like you to see that I have these issues that I need to take care of, fine. And in the cases when I have got this and this, fine, you can see that I will have infinite number of solutions. Why will I have infinite number of solutions? Let us look at it nicely. So, let me put these numbers here, some numbers here. So, let me put alpha here, beta here, D2 here and D3 here, all right. So, this equation tells me that x plus beta z is equal to D3, and the second equation tells me it is y plus alpha z is equal to D2, fine. These two together I can write it as solution as x is equal to D3 minus beta z and y as D2 minus alpha z. So, therefore, if I write x as x y z, this gives me x as D3 minus beta z, D2 minus alpha z and z, which gives me D3, D2, 0 as one solution plus z times minus beta minus alpha 0, fine. And this z is arbitrary, and therefore, I can keep replacing the value of z by 0, 1, 2, e, pi, whatever real number I can think of, and therefore, this gives me infinite number of solutions. This is very important for us to observe and understand that things become very nice when I have got RREF form. I am able to say just by looking at the matrix itself, the RREF, whether it will have infinite number of solutions or not. Because look at this part, the third one, beta and alpha, this does not have a pivot. Similarly, here if I look at, there is no pivot here, all right. So, when you look at the solution set, we will talk about it there. I would also like you to understand here is that, look at how we have got this beta and alpha, fine. So, in this expression there was beta, alpha and 0 coming into play. Here we have got minus beta minus alpha, and this 0 is coming from the z part that we have here. Fine. Sorry, this should have been 1. So, there is a mistake there. So, let me rewrite it correctly. There has to be a 1 here. There has to be a 1 here because it is z here. So, look at here, it is z here. So, you have to be careful. So, z here, when we look at the systems, we will say that the pivotal columns, these are the pivotal columns, they will correspond to what are called basic variables, all right, and these which are free variables. So, these which are not pivot, they will called free variables. So, we will come to that afterwards. Let us not get into that part, but what we are saying is that this gives us all the ideas about solution set in general, all right. So, given a system, go to the augmented matrix, compute its RREF and you have the solution as it is. I have not looked at the case when there is only one non-zero row, please do it yourself, all right. So, now from here I would like you to understand these small theorems which are very important. So, let me write that theorem, and they follow from the idea that the RREF of a matrix is unique, all right. Fine. Let B is equal to EA for some elementary matrix E, all right. Then RREF of B is same as RREF of A. So, whenever I multiply by an elementary matrix, all right, RREF does not change, fine, because B and A are row equivalent. We had just said that if two matrices are row equivalent, their RREF is the same. This is what we are writing and nothing else, fine. You can prove it yourself. This is 1, 2. Now, the next thing that we would like to say is that I already said that if A and B are if A and B are row equivalent, then there exists an invertible matrix P such that P times A is equal to B. We did it for the RREF, because when I am saying that they are row equivalent, I can obtain one from the other by multiplying elementary matrices. The elementary matrices are invertible. So, P is product of elementary matrices which are invertible, all right. So, therefore, P is also invertible. So, I am able to get one invertible matrix, fine. This is the most important part which will help us to define the rank and things like that and proceed us. So, let F is equal to RREF of A, all right, it is given to me, and I have matrix B which has not all the rows of A, but not all the columns of A. I have got only certain columns of. Is that okay? So, I have just picked up some S columns, the first S columns, all right. So, B consists of the first S columns of A, fine. Question is, what can you say about RREF of B? All right, that is the question that we have here. I know that RREF of A is F, B is nothing but the matrix which comes as the first S columns of A. I have just picked up the first S columns. So, what I am doing is that I have an augmented matrix AB, I am just looking at the coefficient part, I am forgetting about B in some sense, all right. So, what we are saying here is that if I pick the first S columns, first is very important, I am not picking any S columns, it is the first S columns that I am picking up. In that case, the RREF of B will be nothing but, so RREF of B will be equal to just look at the first S columns of F, all right. All right. Then this will be happen. Why this is true? Because again the idea is that RREF of a matrix is unique. All right. So, note that since F is RREF of A, F has all the properties or this submatrix which consists of the first S columns of F also has all the properties of being an RREF, and therefore, this result follows. Is that okay? So, I would like you to keep track of this. This is very important idea that you have. Fine. That you are just picking up certain things, certain columns, and everything is nice for you. All right. So, next thing we would like to see is that how do I get the inverse and then relate invertibility with RREF and so on. Fine. So, finding the inverse, of a square matrix. So, what we have learned here is that given a system Ax is equal to B, we can apply RREF to it and get a matrix CD. Fine. So, applying means I am applying it to the augmented matrix and I am getting CD here. Fine. And I can solve it as it is. There is no issue of that. So, in place of just solving the system Ax is equal to B, I would like to solve the system Ax is equal to E1, which is 1 0 0, the first column of the identity matrix. Similarly, I would like to solve the system Ax is equal to E2, which is nothing but 0 1 0 0 0, the second column of I2, and so on till the last Ax is equal to En, which is 0 0 0 and 1, fine, which is nothing but last column. Oh, I wrote it wrongly, this here. So, these are the columns, not the rows, but anyway they are same, but transpose of that. So, first column, second column, and so on, fine. So, let us try to understand what exactly I am trying to do. What I am saying is that I want to solve a system which is Ax is equal to E1, Ax is equal to E2, Ax is equal to En. I want to solve n system of equations. Suppose the solution here is x1, solution here is x2, solution here is xn. Suppose, all right. Suppose these are the solutions for me. Solution is x1, x2 and xn, fine. Let us write the matrix B as x1, x2, xn. I am writing B as whatever the solutions are there for each one of them. I want to compute what is A times B, fine. So, A times B is nothing but A times x1, x2, xn. Now, by matrix multiplication it is same as A times x1, A times x2, A times xn, which is same as x1 was a solution of E1, Ax is equal to E1. So, Ax1 is E1, Ax2 is E2 and Axn is En, and what were En, E1, E2, En? They were nothing but the columns. E1 was the first column of identity, E2 was the second column, En was the last column. So, I do get back identity here, fine. So, what we see here is that A times B is indeed identity, fine. So, let us try to understand this, what exactly I am trying to say. So, what I am saying is that in place of solving the system AB, the augmented matrix, I would like to solve the system A and identity here. I want to solve, so this is an n cross n matrix, this is also an n cross n matrix, and I want to solve it, fine. Is that okay? So, when I want to solve it, the idea is to apply the Gauss-Jordan method and get the RREF, fine. So, what we will do is, we will multiply this by, so what we have seen here is that getting an RREF is same as multiplying by an invertible matrix, fine, which is nothing but product of elementary matrices as such, fine. So, I apply elementary matrices, and so apply elementary matrices and get here some R here and some matrix say E here, all right, fine. When I apply the RR elementary matrices, I will get this, fine. What does this mean here? So, when I am applying elementary matrices, they are invertible. So, I am multiplying certain matrices E1, E2, Ek. Is that okay? Now, as I said, I would like to write it as some P, fine. So, what we are getting here is that P applied to this part is equal to R applied to E. Is that okay? Fine. So, from here what do I get here is that P times A is R and P is same as E. This is very important for us. Look at here, P times identity is E. So, this is very important that you need to understand. Fine. So, what we are saying here is, since P is E, these two together gives me E times A is R. Fine. So, be careful about this. E times A is R. And what is E? E is nothing but P, and P is invertible. Why is P invertible? Invertible because P is product of elementary matrices. Fine. So, again let us understand that I have A and identity, I started with that, I am applying elementary matrices, I have got R comma E, fine. So, what I am doing is that I have multiplied elementary matrices, say E1, E2, Ek with us. This I am writing it as P, I wrote it as P, fine. So, P times A of I and A and In gives me R comma E. I look at the two matrices separately, it gives me P times A is R and P is E. Since P is E, these two together gives me E times A is R, fine. And P is product of elementary matrices, so P is invertible, so E is invertible, fine. E is invertible. That is very, very important, all right. Now, what can I say about R? Let us try to understand that, fine. So, let me write it here before going to the next page. So, what we are saying is that E is invertible. Now, if I look at A, so what we had learnt was that, let me go back here, that let F be equal to this, B is equal to this, the first S columns, all right. B consists of the first S columns of A. Then the RREF of B, this new matrix, is nothing but the first S columns of RREF of A itself, all right. It is just the first S columns here, this is what it is, fine. So, what we are saying is that if this is the RREF of A and In, then R is the RREF of, so this implies by the previous theorem that R is indeed equal to RREF of A, fine. So, please go back to the previous one again, let us see, it says that F is the RREF of A. So, for us in this example what we have is F is equal to RREF of this, fine, which is nothing but R and E. This is what we wrote it as, fine. So, RREF of A and In was this, and therefore, I am looking at A, the first n columns, the first n columns of this matrix, and therefore, its RREF, all right. So, the RREF of A has to be this part. Is that okay? This is what it says, the first S column, the first n columns of F. So, the first n columns of F, which is nothing but R, fine. So, this is what is important, you get R equal to RREF. Therefore, if R is identity, then E times A is identity. Look at this part from here, E times A is R, R I am saying is identity. So, E times A is identity, E is invertible, implies E times A is equal to I is equal to A times E, and therefore A is invertible. Fine. So, when I apply RREF to A and this, and it turns out that the left hand side, this R turns out to be identity, fine. If it turns out to be identity, then I know that the right hand side is the inverse of A, and if R is not the identity, then I know that A is not invertible. All right. So, let me write that part. So, what we have done is I have A and identity with me, applied the Gauss-Jordan method, which gives us, all right, the Gauss-Jordan method which gives us the RREF. This is supposed to be R and E. If R is identity, then A inverse is E. If R is not equal to IN, then A is not invertible. So, we are getting both of them at the same time. Is that okay? Fine. So, let me just explain this with a small example, how to compute this inverse. So, example. So, I have the matrix A as 0 0 1 0 1 1 1 1 1. This is the matrix I have. I want to see whether this matrix is invertible or not. If it is invertible, find its inverse. So, we write A and I3, which is nothing but 0 0 1 0 1 1 1 1 1 1 0 0 0 1 0 0 0 1. Fine. I want this to be the pivot for me. So, I have to interchange these two. I am not going to write that part. So, let me write one after the other. So, I want to make this as the first row 1 1 1 0 0 1. Fine. 0 1 1 0 1 0 0 0 1 1 0 0. I have this. So, interchange third and first row. All right. Important thing is I am allowed only row operations, no column operations. All right. Fine. At the next stage, I can use this one to make this entry 0. Fine. So, I have 0 0 1 1 0 0. Use this one to make this entry 0, or use this to make this one 0. So, let me do that. So, I can make 1 0 0, all right, this minus this. So, become 0 0 here, it will become 0 0 minus 1 is minus 1, 1 will remain as it is. I can make this 0 using this. So, I will get this minus this. So, I will get here minus 1. Is this correct? I hope 0 here. All right. Yes. Fine. So, what I have done here is R3 R1 is being replaced by R1 minus R2. So, just look at this, this minus this will give me 0 here, 0 0 minus 1 and 1, and I have also done after that. Once I have done this, I am looking at R2 is being replaced by R2 minus R3. This minus this, so get minus 1 1 0. All right. So, for me what I see is that this is I3. So, this is the inverse. So, you can check that 0 0 1 0 1 1 1 1 1, this matrix times 0 minus 1 1 minus 1 1 0 1 0 0 is identity. All right. The way to check is, look at this, it says that you are looking at 0 times the first column plus minus 1 times the second column plus 1 times the third column. So, here it says 1 will remain as it is, the first part will remain 1, minus 1 will give me 0 0 here. If you look at this, it says minus 1 times 0 0 1 plus 1 times 0 1 1. So, this gives me 0, this 0, this 1, this gives me 1, minus 1 plus 1 again gives me 0 here, and this gives me 0 0 1. So, it is indeed the inverse. Fine. So, I would like you to learn to compute these things, all right, and it is very very important that I start with A and IN. I apply the Gauss-Jordan method. If the first part has identity as an RREF, then I get the inverse, otherwise A is not invertible. Thank you.